Example 7. Carbon dioxide in the atmosphere traps heat from the sun. The additional solar radiation trapped by carbon dioxide is radiative forcing, and it's measured in watts per square meter. We can model this radiative forcing using this logarithmic equation right here. C0 is the pre-industrial amount of carbon dioxide, C is the current carbon dioxide, and K is a constant. Part A says, suppose that C equals 2CO and K is 14. Find the radiative forcing under these conditions. So look at your equation. R equals K is 14 times the natural log of C was equal to 2C0 over C0. Well, conveniently, those two cancel out, and so I'm looking at 14 natural log of 2. Which is 9.7, about 9.7. Remember, our units up above were watts per square meter. Part B, the average global temperature increase in Fahrenheit, in degrees Fahrenheit, is given by T of R. That's not multiplication, that's a function. T of R equals 1.03 times R. So that is multiplication. Find the average global temperature increase to the nearest degree Fahrenheit. So we've got this equation, or this function, T of R is equal to 1.03 times R. But R is what we just found in part A. R, according to our calculations, was 9.7 watts per meter squared. So we're just going to multiply 1.03 times 9.7. We get 9.991 degrees, or about 10 degrees. So that's the average global temperature increase. Oh, probably should say that's in Fahrenheit. About 10 degrees Fahrenheit. Change of base theorem. This is important. You're probably going to want to memorize this, and it looks a lot harder than it actually is. Once we get some examples, you'll see how easy it is. But basically, what happens is the calculator only has one log button. Well, I guess it has two log buttons. It has the common log and the natural log. And so what this formula does is it allows me to take any other base other than base 10 or base E and convert to something I can plug in on a calculator. Example 8 says, use the change of base theorem to find an approximation to 4 decimal places. So when I see log base 4 of 20, all this formula says that I can do is I can go log 20 over log 4. So I changed it into log base 10. Log base 10 of 20 over log base 4. Or you can actually do the same thing with the natural log, and it would give you the same exact result. So your choice, one or the other. I like log. Some other people like ln. So let's see what the calculator says. If I do log 20 over log 4, you get about 2.1610. If I do natural log of 20 over natural log of 4, you get the same thing. So your choice, one or the other, you get the same thing. So then for log base 2 of 7, log 7 over log 2. And this just makes it easy to do on a calculator because you couldn't plug in a log base 2. There's no log base 2 button on a calculator, but there is a log base 10. So I'm doing a common log, or log base 10 of 7 divided by log base 10 of 2 gets about 2.8074. Now, as a side note to this, keep in mind what we're finding here. If you get an easier one, like log base 2 of 32, let's say, all right, we did these in a previous lesson, you should be able to do this one in your head, because remember what we're finding. The answer to a log is the exponent. So you're thinking base 2 has an exponent of something, that's this, to give me 32. And so 2 to what power equals 32? Well, 2 to the 5th power. And so log base 2 of 32 is 5. I'm finding the exponent. When I'm finding a log, I'm finding the exponent. So when I do one of these problems, think of this as base 2 to the 2.8074 is equal to 7. All right, I'm finding the exponent. So let's just see. 2 to the 2.807354922058 gives me 7, sure enough. So keep in mind, when you're finding a logarithm, you're finding the exponent. Okay, one measure of the diversity of species in an ecological community is modeled by this formula, where the P are the proportions of a sample that belong to each N species. So example 9, we're going to use that formula. Find the measure of diversity in a community with 2 species where there are 60 of one and 140 of the other. So if you notice, you need to find the total number N. It looks like there are 200 total. But P1 is going to be the proportion of this one. 60 over 200 is 0.3. And P2 is going to be the proportion of the other one. 140 over 200 is 0.7. So if there are more than 2 species, you'd have to do that calculation for each of the species, but we only have 2, so that's all we have to do. Now we have to plug into the H formula that I've got boxed in above. So H equals negative, P1 is 0.3 times log base 2 of 0.3 plus 0.7 times log base 2 of 0.7. So it will be a calculator question, but I'm going to have to use that change of base formula. Okay, so go back and look at your change of base formula. Change of base formula. We'll have negative 0.3, and then here's where we're going to change the base. You'll have log of 0.3 over log of 2 plus 0.7, change of base formula, log 0.7 over log 2, close it. So here I've got it typed in, negative quantity 0.3, and then you can see where I did my change of base formula here, log 0.3 over log 2, and here's another change of base formula. So typed all that in. I got 0.881, about 0.881. So whatever that number means, that's the measure of the diversity in a community of these species.